Section 5.5 puts it all together. So we take all of the exponential rules, all the logarithm rules, and we use those so that we can actually solve equations. So what we want to do in this section is remember a few things. So let's recall that if a equals a to the y, then y equals log base a of x. Because y is an exponent, y is the exponent, and logarithms are exponents. So number 1. Number 2, the inverse of a to the x is a logarithm. So let's see number 2. The inverse of, if f of x equals a to the x, then its inverse, f inverse of x, equals log base a of x. So x was an exponent here, but now it's the argument, and I got a little crazy there. We have to have the same base. So a is the base, shown as a base here, shown as a base here. This is the input. Remember how when we graph this backwards? So we put in y as an exponent instead of x because it was hard to put in the argument here. And because of this, that means that if you take this exponential, but you say log base a of that exponential, the logarithm and the exponent cancel out and you get x, which is what happens when you undo. So inverses undo, and your goal is to get x out. And this gives you x. And vice versa, if you had a logarithm but you made it the exponent of an exponential, then this is an exponential raised to a logarithm. They undo each other, and so again you get x. It simplifies to x. We learned logarithm properties. We learned that log base a of xy equals log base a of x plus log base a of y. And same thing with division. So we learned log base a of x over y is equal to log base a of x minus log base a of y. And we learned the power rule, which is that log base a of x to the r power is equal to r times log base a of x. So it turns into multiplication. So that's a review of all the rules that we've learned so far. This we learned when we finally got into logarithms. We drew the graphs to see that they reflected over the line y equals x, which is this undoes factor. We learned these properties in, so this was 5.3, this was 5.3, this is 5.4. And now we're in 5.5. We're going to use all of those rules in order to solve equations. So our first equation here is 3 to the 2x minus 5 equals 11. We're going to solve this first by leaving our answer in an exact form, kind of like when we leave pi and geometric answers, or we left e and other things when we simplified them. So we're going to leave natural log or logarithm in our final answer, so we're not going to round. So what do we do here? We can't make 3 and 11 have the same base. This is not 3 and 9, which we would have solved in the very first section that we did with exponentials. So we can't do that here. We have to rewrite it another way. So there's two ways to do this. First, you can take it to base 3 and simplify that way. You can take anything to the natural log base. So we're going to start that way. We're going to take this side to, I should change to a different color. So I'm going to take this side, I'm going to say the natural log of 3 to the 2x minus 5 and the natural log of 11. Exponent rules say that I can take this exponent and put it in the front as multiplication, so that's 2x minus 5, the entire thing, times the natural log of 3, equal to the natural log of 11. I need to get this part by itself before I can do anything else. So I'm going to divide both sides by the natural log of 3. And so I now have 2x minus 5 equals the natural log of 11. So the natural log of 11 over the natural log of 3. Now this is not the same thing as this rule up here. I have the natural log written twice. That means they're completely separate logarithms. I cannot apply this rule. Notice this has one logarithm separated into two with division, its division, so it goes to subtraction. This one you can't do it because this is the natural log of 11, not the natural log of 11 thirds. Anyway, I need to add 5 to both sides, so plus 5, and this one is canceled, and then divide everything by 2, or multiply both sides by a half. So now I can multiply both sides by a half. It's the entire side, so everything gets distributed by a half. These cancel. Now we have x equals the natural log of 11 over 2, the natural log of 3, because 1/2 times this, plus 5 halves. So this is the exact answer. In order to find out a decimal approximation, you can type this in your calculator just as it is. So in my calculator, I would have, I'm going to do a fraction, I would have natural log of 11, parentheses, 2 natural log of 3, and then plus 5 halves. I'm just going to put 2.5, and that will give me 3.591. X equals is approximately 3.591. So this is the approximate answer from the calculator. You could confirm that with a graph. You could graph 3 to the 2x minus 5 equals 11 and find out where they intersect. They would intersect at the x value, 3.591. There's another way to work this exact same problem. So if I wrote down the problem that I just did a minute ago for number 1. If I decide, instead of taking the natural log of both sides, what if I took log base 3? So log base 3 of both sides. I have to do the same base, so I have to choose one and go with it. If I choose log base 3, what happens on this side is that I have log base 3 and a base of 3. They cancel each other out, and 2x minus 5 now doesn't have any logarithms at all. On this side, I have log base 3 of 11. Now we can add 5 to both sides. We have 2x equals log base 3 of 11 plus 5. Divide everything by 2. I'm going to divide this one by 2 and this one by 2. So x equals log base 3 of 11 over 2 plus 5 halves. Now, does this equal what I had before? And it does, because if you use the change of base here, that's going to be, I'm going to rephrase it as 1/2 for the divided by 2. And then if I change log base 3 of 11 to natural log of 11 over natural log of 3, that's the change of base equation, plus 5 halves, I get exactly what I had before for my exact answer for this problem. So it's up to you, as long as you take the same log to both sides. So you can do same base 3 to both sides. In the first example, I chose the natural log to both sides. As long as it's the same one to both sides, you can solve the equation that way. I suggest sometimes it's easier to keep the exact answer until the very end so that you don't have long decimals that you're trying to simplify if you're doing a calculator approximation. Let's try a new problem. Again, we don't have the same bases in this problem. It says 5 raised to the power of 3x minus 1 equals 2 raised to the power x plus 3. So we can't solve this like we did in 5.1 where we got the same base. What we need to do is choose a logarithm so that we can simplify this. Most students choose a base that is one of these two bases so that they can simplify it from there. and it's just up to you. You could choose, okay, I want to do natural log of both sides and work it that way. You could choose log base 5 so that something simplifies. It's really up to you how you choose to work the problem. I'm going to choose the natural log for this because natural log is probably actually the easiest to use for any of them. It's shorter to write and is what we're going to use in calculus most, the natural log function. So if I take the natural log of this side and the natural log of this side, I now have a way to rewrite this exponent not as an exponent. Logarithm rules say that I can take the exponent and write it in the front. 3x minus 1 times the natural log of 5 equals, same thing here, x plus 3 times the natural log of 2. Now, in trying to get x by itself, I have to do some fancy mathematics. This is not going to be your favorite, but mathematically speaking, it's not difficult. It just looks really long. So we need to distribute because I need to get x by itself, which means I need x on the same side. I'm going to need to factor. When we learned in Algebra 2 that if x is written twice, we need to factor. That applies here. We're going to have to factor to solve this. But in order to get x by itself, we need to distribute it out. So we're going to end up with 3x, the natural log of 5, minus the natural log of 5, equals x, the natural log of 2, plus 3, the natural log of 2. So I have distributed the natural log of 2 over everything, and the same with the natural log of 5. So now what I want to do is get all the x's on one side and all the things with x's on the other side. So I'm going to say I have 3x, the natural log of 5, this stays on the left. I'm going to put x natural log of 2 on the left, so it'll be negative x natural log of 2. I'm going to move natural log of 5 over here, so it's positive plus 3 natural log of 2. Now we have x on the same side. Our rule is if it's written twice, we have to factor it. We're going to take it out, so that leaves 3 natural log of 5 minus natural log of 2. We took the x out of both. Here it is, taken out, equals the natural log of 5 plus 3 natural log of 2. There's a lot of writing here, but that's not difficult. Writing is not difficult. And the math is very Algebra 2. It just looks really long because of all the natural logs. What do you do when something's multiplied by x? You divide by this entire binomial, 3 natural log of 5 minus the natural log of 2. So I have what x equals. X equals, and we could put this in our calculator. The natural log of 5 is a number. 3 natural log of 2 is a number. 3 natural log of 5 minus natural log of 2. This is all something you could put in your calculator. So let's do that. I think the easiest way, if you've got this calculator, is to make a fraction. So alpha x gives you fraction. We can type it in just like this. Natural log of 5 plus, and I need to clear that, the natural log of 5, I need to close my parentheses so that I don't have composition of functions, plus 3 natural log of 2, close parentheses, 3 natural log of 5, close parentheses, minus natural log of 2, close parentheses. And now that I have it all top, and bottom, then I can solve for it, and I've got 0.892. So this is approximately 0.892. And this, even though it was gross, was easy to put in the calculator. So x equals 0.892. Sometimes the equations will surprise you. So in this example, example 3, this was actually doable in an earlier lesson. Look closely, it has a base, an argument, and an exponent. You can rewrite this and solve it simply without even having a calculator. So Hamburger Helper says 7 to the power of 2 equals 3x minus 2, which is simply 49 equals 3x minus 2. Add 2 to both sides, 51 equals 3x. Divide by 3. 3 goes into 5 once and then 21. So x equals 17. So sometimes you have to evaluate it based on you're going to have to figure out what puzzle pieces you have. In this case, it is simply rewriting it as an exponential that will make this easy to solve. But in this problem, we have many more logarithms shown, so it's not just logarithm on one side. We need to simplify this so that we have just one logarithm, so we need to condense them into one. So I'm going to keep the left-hand side as log base 5 of x. And on the right-hand side, I'm going to use this minus to combine them with exponent rules. So it's log base 5, but subtract means they're 2x plus 3, and then 2x minus 3 is in the denominator. So minus means division rules. So now we can think about this problem the same way we would have considered 2 to the x equals 2 to the 4th. If the bases are the same, then x equals 4. The exponents are the same. Here we have the same logarithm base, so we can drop the logarithms and solve x equals 2x plus 3 over 2x minus 3. In order to solve this, we're going to use cross multiplication. X times 2x minus 3 equals 2x plus 3. Distribute 2x squared minus 3x equals 2x plus 3. We're going to get them on the same side, so 2x squared minus 5x minus 3 equals 0. So I need to subtract my values, and I know that 2x only has the one choice. So 2x and x represent 2x. 3 is either going to be here or here, but I have to subtract values, which means I need 6 minus 1. So minus 6x plus 1x makes 5. My solutions are negative 1/2 and 3. But just like square root functions, this has a limited domain. The domain for x is that it has to be greater than 0, and that means that negative 1/2 is excluded right away. So the only answer for this one is 3. Does 3 work? 3 is positive here. 6 plus 3 would be positive here. 6 minus 3 would be positive here. So 3 is okay. That would be our solution for number 4. There are many other ways to solve these equations, many other types of problems that you can see. But for this first practice assignment, I think I've covered examples that are similar to most of the types that you'll see in the homework. You might have to take something like e to the 2 natural log of 4 and rewrite it. So note that you need to know all of the rules for the inverse functions and exponents in order to make this something that's more simple. So I could say this is e to the natural log of 4 squared. Just looking at this piece, the 2 can go up here, can go backwards and become a square. Now note that this is the base e and the base e. These cancel, and this simplifies to be 16. So there are little things that you might have to simplify within your equation before you go and do the math like this. So there are many different kinds of problems to try to solve. They're all different kind of puzzles. So evaluate what kind of puzzle pieces you have and how you can work that into an equation. Note whether it wants exact answers or whether they want you to put it in a calculator to solve. So you can check your odds and find out what kind of answers you're looking for. We will do more of this in our next lesson and see other types of examples and then go over any questions that you have. So bring your questions, but you must try. These will not come to you if you don't give it a shot. So think about it as far as writing a unicycle. You'll never be able to do that if you don't give it a couple of tries. And sometimes you might fall down, but you have to get up and try again, and eventually you'll be able to succeed at whatever you try. But try, okay? And then we'll go over any questions and see if we can make any, words of wisdom that help you see what trick it is to solve each particular puzzle. All right, good luck. See you for next lesson.